So, welcome everyone to lecture number 15 of the lecture Statistical Theory for Deep Learning. As always, I start with a slide where I repeat what we did last time. We introduced the notion of VC dimension of a set of subsets of RD. And this VC dimension is the maximal number of points which can be shattered by this set calligraphic A. So it's the supremum of all natural numbers. So that's the nth shatter coefficient of A, which is the maximal number of subsets of a set of n points in RD, which can be picked out by A, such that this nth shatter coefficient is 2 to the power n. And then we have seen the following bound on this nth shatter coefficient, or then we have seen derived a bound on this nth shatter coefficient depending on the VC dimension. If calligraphic A is a subset of, as a set of subsets of RD, then the nth shatter coefficient of A is less equal the sum I equal 1 to the Fabry-Javanakis dimension of A and the binomial coefficient of M and I. So you see the right hand side is if the Fabry-Javanakis dimension of A is less than infinity, then the right hand side is a polynomial in n of degree at most Fabry-Javanakis dimension of E and A, and this gives you the surprising consequence that either you have this n shatter coefficient is 2 to the power n for all n, or this n shatter coefficient grows as a function of n only polynomial. I've also prepared a few exam questions again, which I can show you. Where is it? Should be somewhere here. Maybe these are these questions here. Correct. Not sure. Let me see. Yeah. Okay, I think it's correct. So it's just one new question, question number 18. Let A be a non-empty class of sets, A subset of RD. How is the VC dimension of A defined, and how can it be used to bound the nth shatter coefficient of A? So you have to present this bound of theorem 3.4. And next I will present the consequence of theorem 3.4. Maybe it makes sense to show theorem 3.4 again. It was maybe this guy. That should be the slide of the beginning, correct. And I will present the corollary, which we will use further on. It's corollary 3.1. Let A be a set of subset of RD with VC dimension phi A. Let A be a set of subsets of RD with VC dimension Then I present two bounds. The first one is the n shatter coefficient of A is less equal n plus 1 with exponent VA. first bound, and the second bound, if you have n is greater or equal than the VC dimension of A, then we get n is less equal E times n divided by VC dimension of A. VC dimension of A for all n greater than or equal to the VC dimension. And the proof is simple. You just show that the right-hand side of theorem 3.4, which is now bound on the left-hand side of corollary 3.1, is less equal than the right-hand side of corollary 3.1. So let's do it. We look at SARN. We know by theorem 3.4 that's less equal to the sum of these binomial coefficients. Sum is going from 0 to VC dimension of A. And the binomial coefficient, Ni. Then you know its definitions. This is n times n minus 1 times n minus I plus 1 divided by faculty. I upper bound each of these factors n in the nominator by, or each of these factors n minus j plus 1 in the denominator by n, so it's less equal than and I want to add, I want to get an n plus 1 as exponent VA. You use the binomial theorem to represent this as a sum from I equal 1 to VA, and then you have to add here, somehow you have this n over I, we have it already, but you need some binomial coefficient. So you make an upper bound again by adding VC dimension of A times C dimension minus 1 times VC dimension minus I plus 1. And if I runs from 0 to VC dimension of A, then all of these factors are greater or equal than 1. Then you see we have I equals 0 to VA, this binomial coefficient. And that's just by the binomial theory, that's just n plus 1 is exponent VA. And that's what I wanted to show. So, okay. First part, done. Then the second part, we assume that n is greater or equal than the Z dimension of A. And I multiply the whole inequality by VC dimension of A divided by n with exponent VC dimension of A. So I look at VC dimension of A divided by n with exponent VC dimension of A, and multiply this with SAN. And then make an upper bound such that this is less equal than E with exponent VC dimension of A. Then, here comes the question.
E is defined how?
E is the Eulership number.
Okay.
The usual 2.7 more than so on. And then we say the sum of n equals 0 to infinity 1 divided by n from t. Okay, we use again our previous theorem. Then I got this guy divided by n with exponent sky times the sum. It was a number coefficient. I multiply this first factor in the sum, and then I make, because VC dimension of A divided by n is by assumption less equal 1, I make it smaller by just making this exponent. No, I make it larger by making this exponent smaller. So I have a VC dimension of A divided by n is exponent I times n over I. And this upper bound. Then I increase the upper bound in the sum. All these terms in the sum are non-negative. I replace which are latest dimension by n. And then I use the binomial theorem again and consider instead 1 plus the dimension of A divided by n is exponent n. And if you apply the binomial theorem to the right hand side, then you see just to the left hand side. Question?
Aren't we divided by 0?
Aren't we divided by 0? I divide by 0, yeah. And that's because I wrote it in the wrong way, yeah. Sorry guys. There's a kind of typing error. And you know that there are different kinds of typing errors. There are typing errors. Okay, how to say it in English? It makes the proof hard to understand. There are typing errors which are obvious. Don't know what this is here. I usually do it if I mark some exams. If I mark some master thesis here, then I mark every typing error we do. And then sometimes I'm writing, okay, in the journal, Sinn entstellt. Because if you don't, well, this is something close to it. But it's obvious what I did wrong here. I have to just add what I have here. Should do it this way. And then you see, thank you. Now you know that 1 plus x is less equal to the power x for all x, for all r. See it if you make a graph of 1 plus x, and if you plot e to the power x, obvious. You plug this in with x is equal to VC dimension of A divided by n, then we get an e to the power Vc dimension of A divided by n times n, and I got what I want to get. This is e to the power Vc dimension of A. And that's what I wanted to get. Questions? Then I can turn this off. We don't need it anymore. So now we have a bound on the nth shadow coefficient. As you have seen last week for our motivation, this nth shadow coefficient can be used to bound packing numbers of sets of indicator functions. But what we actually want to get is we want to get a bound on packing numbers. So that's what I'll derive next. Here. So if I have a set G of functions, G be a set of functions, say we have d equal 1, I have x, I have g of x, we put sometimes in this. And then I use, for this one, because I want to use some kind of dimension of the set of functions, and it turns out the right thing to do to define this dimension of this set of functions. We have just learned about the Vc dimension, which was the dimension of a set of sets. Yeah? And I look at the subsets of all graphs of this function, and these graphs are just the function set of points which are below below or subgraphs. Yeah. Subgraphs of function. Yeah? You have the graph of the function, and the subgraph is just the set of functions below. And this is G plus. And formally, it's a set of sets, and the set of sets, you have one set for each function in G, and the set consists of T in D times R, such that T is less equal to x. And G is in G. And then you see here, you have just this set of all xt in R times R, where T is less equal than G of x. And for this set of subgraphs, we have now already defined, it's a set of sets. We have defined the Vc dimension, and it turns out I can use this Vc dimension to bound the packing number of G. And that's my next theorem. Classical result from Hausler. Okay, I had this time, I replaced the t by an L, at L and N. I consider bounded functions where the function value is bounded from above by some p greater 0. G, a set of functions G from R1 to 0B. And I assume that this Doppler moment is dimension of G plus is at least 2. Then we have for any probability measure mu on RL. And any radius epsilon, which is at most b divided by 4. And of course greater than 0. 0 is less equal to epsilon divided by b divided by 4. I look at the L1 epsilon packing number of G with respect to the, or I look at the epsilon packing number of G with respect to the L1 norm introduced by mu. And we have the following upper bound. It's less than 3 times something with exponential, this exponent public Cherenkis dimension of G plus. And the something is 2e e divided by epsilon times the logarithm of 3EB. And the whole thing is exponent of the Cherenkis dimension of G plus. And that's the point here. So see, as soon as you know the Vapnik-Cherenkis dimension of the classified subclass of G, you can give an upper bound on the packing number. This is the L1 of nu norm. You can easily also generalize it to the LP of nu norm by using that there's some relation between the packings with some radius in the LP norm and packing with some radius in the L1 norm. You will do this in the practicing course. I think in 3 weeks or something like this, 2 or 3 weeks. But I will focus here on the L1 bound. Questions? Okay, then we have a kind of problem because we have to prove it. And this is, again, something non-trivial. But it's a nice proof, as you will see. And somehow I will use corollary 3(1)b in order to do it. Any questions?
The logarithm to which base?
E. Okay. Logarithm is always the natural logarithm, as long as I don't write something else. So what I will do, I will well, let's do it and you will see. Maybe I'll start with the proof, then I'll explain it. Maybe it's better if I look at my lecture notes. It's the first line of the proof, then I can explain what the proof. We will show, and that's the insertion. I will show a connection between the packing number and some shatter coefficient involving the packing number. More precisely, I show that my epsilon packing number G is less equal than 3 times the shatter coefficient of G plus. And the number of points involves the packing number, but not the packing number, instead on the logarithmically packing number. More precisely, the ceiling floor, so we truncate from below, e divided by epsilon times logarithm of 2 times the packing number again. So I show this relation. That's the main trick. And then there are two questions. First question is, how does this imply the assertion? Second question is, how to show this. Let me start with the first question. This implies the assertion because I will apply on the right hand side my corollary 3.1b, which gives you, if this n is greater than the VC dimension. Well, yeah. Okay, let's do it. This implies the assertion. I make two different cases. The first case is that I can apply my corollary 3.1b, which means that my n, and my n is this Gauss bracket here of the logarithm of the 2 times the packing number. If this is greater than the Wapnick-Jovanekis dimension of my class of Z, which is the set of a subclass, then we can conclude from corollary 3.1 3.1b. I get some less bound. Maybe I get them. I get that my this one is upper bounded by this, so the left hand side here, packing number, G is less equal than the right hand side here. The right hand side here is E times N. My N is the Oh yeah, no. But there's a 3 here, yeah? Oh, 3 times. Now I have to write in my scatter coefficient and with the n, but with the n I can also forget about this gauss brackets here because this makes this number smaller. So that a little bit larger. We have d times this, and I forget about the gauss bracket. Epsilon times log 2 times yeah, and I have a kind of problem here divided by the Cherenkis dimension. Graph for subgraphs with exponent is the Cherenkis dimension of the class of all subgraphs. So we have this one. So I just applied corollary 3.1b and I upper bounded this lower Gauss bracket by the bundle itself. So that's fine. And now what do you have here? You have some number which is less than some polynomial of a log of this number. And then you can imagine this number can't be arbitrarily large because the linear function is growing much faster than any polynomial of an algorithm. So by using and that's the next trick here. Let me clean it backward before. If I could open this somewhere. Now we use that if I have some x is less equal than 3 times e divided by b times log 2x is exponent b. That implies x is less equal than 3 times 2a times log 3a with exponent b. And somehow we have to match this one with the other one, so somehow we have to decide what is a and b. And maybe you can help me here. If you want to, and that's my relation star star. And if you look at the, well, of course, x is the packing number, yeah? But what is a and b?
The small b should be the VC dimension.
The small b is the VC dimension of the class of subclass.
Yeah, and a should be the factors, so
E times
divided by
epsilon. And then you see what you get is you get that this packing number is less than 3 times 2 times E times B divided by epsilon times the logarithms of 3 times E times B divided by epsilon with exponent BC dimension, and that's exactly what we have here. Yeah? We get answers. Does this help us? Well, not really, because now we just have reformulated one point to another. Now we have to, of course, we still have gap, because why does this hold here? Yes. Yeah, and maybe you see it. I would like to reformulate this guy here, and I would like to use that in the log is each time the same, so 2x, so I add a factor 2 here, and I replace the 3 by 6, and then I replace this b in the logarithm by 2x with exponent 1 over b, and this b on the other side. So star star is equivalent to 2. You see we have, I want on the left hand side, I want something like 2x with exponent 1 over b. That's less equal than something where on the right hand side I also have a logarithm of 2x. 2x is exponent 1 over b, and I replace this by a new variable u, and now you have to be careful what you need on the right hand side. Well, I have to multiply by 2, then the 3 gets a 6. I have to take the b's root, then you have a 6 with exponent 1 over b. And I think there should be a and this implies well, I also write the so also I replace here the x by 2x with exponent b, 1 over b, and then you need to multiply by 2 and take the root. So it's again 6 1 over b times that's here times 2a times log b. That should be the same. Correct? Not correct? That looks You see this question?
Yes. Where's the divided by b?
Excuse me?
In 2 star, we had a divided by b, and now we only have an a.
Well, this is 1 divided by b, and this enters the logarithm as logarithm of 2x with exponent 1 divided by b. Rule for logarithm.
Yeah.
It enters here. Because you have, it's here.
Mhm. Okay. Mhm.
Okay? Now I reformulate this by setting this equal to u. This follows from, and that's 3 star. So we have, and I set this guy equal to c, u as equal to c times log u implies, and I want to show that this implies u is less equal than 2c times log c. Well, I wanted to show, but there's an additional. Okay, I think something. Maybe we figured it out. This is, well, it's elementary maths, yeah? It should be analysis 1, basically. I want to show this one, what is C. Can me anyone tell you what C is?
It should be 6 to the power of 1 divided by b times 8.
6 to the power 1 over b times 8. And then this is fine, yeah? Here. This here fits too, yeah? But what about this 3c here? Well, if you look at this log 3a, what I actually want to get is, I want to reduce it to c, so it's a logarithm of 6 exponent 1 over b times a divided by 6 exponent 1 divided by b times 3. And now I want to forget about this 3 divided by 6 is 6.1 over b. I will just upper bound this by 1. Then the question is 6 to the power is 3 times doesn't look right to me here. Any idea? Please.
If we know 3 star, then we can say the left hand side is less than equal whatever we plug in but with log C instead of log 3a. So if we can show log C
Okay.
is less than equal log 3a, then we are fine, right?
If log C is less equal than log,
3a.
so basically 3 should be less equal than 3a, right? That's what you,
Yes, and with the C that we have above. And then we
and
use
then if you can plug in what C is. C is
6 to the power of 1 divided by b times a.
good point. 6 to the power 1 and b times a is less equal than 3a. And this is true. Why is this true?
Because b is the VC dimension, which we assume to be greater equal to 2.
Because b is greater equal than 2. Sorry for that. A little bit confusing. But you see what I did here? Yeah. So reduced one inequality to another inequality to another inequality, or another implication, yeah? And now we can also look how large is C. It's 6 exponent 1 divided by b times a. A is e times b divided by epsilon. And we had something that epsilon is less than b divided by 4. So that guy, of course, this guy is greater equal than 1, and a is greater equal to e. So that's greater equal than e. So we have to show that for any u in the positive numbers and any c greater equal than e, u less equal c times log u is less equal than u less equal to c times log c. Please?
Is it an if and only if that if C is smaller or equal than 3a, then it also has to hold that 6 to the power of 1 divided by b and have a is smaller or equal
Good point,
to
good
3a.
point. I think, no, I don't want to, I don't want an if and only if here. You are perfectly right. We want to get what we want to get. We want to show that,
Shouldn't those two events be independent?
I think it's just this guy, no? Oh no, this direction. What? We wanted to prove that C is less equal than 3a. So I need this direction. This direction was true. Yeah? Because okay, we proved this guy here. We proved this 3 star here. Then you have the left-hand side of the implication you want to show is true here. So we get the right-hand side, this one is true, so we get this one, the right-hand side of 3 star is true. Then we plug in our C, and then I want to, this guy I have here, but I want to have here 3a. So I need that the logarithm of C is less equal than the logarithm of 3a, which is equivalent to that C is less equal than 3a. And that we get because this is. Okay? Yeah, maybe now you see why the proof is not in my lecture notes. It's elementary. Well, we started with, where did we start? I started with one inequality, then, or maybe let's make a break for 5 minutes. And so it's 10:40, so I go on at 10:45. like to go on. So let's repeat, what are you doing? We are trying to derive an upper bound on a packing number using the VC dimension of the set of all subgraphs. We are doing this by relating the packing number to some shatter coefficient of the set of all subgraphs involving a logarithm of the packing number. We apply corollary 3.1b, which requires some condition, which we have to discuss whether it's satisfied or not, or what to do if it's not. And then we see that we get some relation between the packing number is less than something times the log of the covering number of the packing number divided by the VC dimension with exponent VC dimension. This is of the form x is less equal than 3 times a divided by b times log 2x with exponent b. With a and b here, we show that this implies x is less equal than 3 times 2a times log 3a with exponent b. From this, we get immediately the assertion. So we have to prove this star star. To prove this star star, we rewrite the whole thing a little bit, write it as a function of 2x with exponent 1 over b, and then we see, after some tedious considerations, that basically what we have to show is that if for a non-negative number or a positive number u, and for some c greater or equal than e, if u is less equal than c times log u, then u is less equal than 2c times log c. And this makes sense because if u, of course, grows much faster than the logarithm of u. Yeah? So if you have such a relation, then there must be an upper bound on u. The only question is whether this upper bound is the correct one. Now, you make a contraposition and see. So it remains to prove star star star. This star 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 is equivalent to, and we just make the contraposition if u is greater than. So if the right hand side does not hold, then the left hand side does not hold. If u is greater than 2c times log c, this implies that u is greater than c times log u. And this is what I call star star star, 4 star. And to prove this, you on the right hand side you have two functions. F1 of u, let F1 of u equal u, F2 of u is equal c times log u, and you want to prove that F1 of u is greater than F2 of u if u is greater than 2c times log c. And we show this by showing that the derivative of F1 of u is greater than the derivative of F2 of u. And star follows from well, actually show at the point 2c times log c, F1 of u, so F1 of 2c times log c is greater than F2 of 2c times log c. At this point it's satisfied, and in addition F1 grows faster than F2. greater than 2 prime of u, u greater than 2c times log c. So again, I had one assertion and I reduced it to 2 other assertions. But these, the advantage is these 2 other assertions are now easier. Forget about this one. Look at this derivative. What about derivative? You see it? What's f1? Phi prime? 1 prime phi? Well, what's the c prime of u?
C divided by u.
C divided by u. Now, and if you have u is greater than 2c times log c, then you see that this is less than c divided by 2c times log c, for u greater than 2c times log c, which is 1/2 times 1 divided by log c. And now the question is this less than 1? And this is less than 1 because? Well, you can see that I have a secret plan for this lecture. So you would say I'm knowing what I'm doing because we had this assertion that c is greater than equal than e. If c is greater than equal than e, then log c will be at least 1, and then this is of course less than 1. And c greater than e. So that's great. The negative condition holds. So now what's going to do is you have to see and look at this. You have to see that 2c times log c is greater than c times logarithm of 2c times log c. And that's elementary. Completely fun. Well, shall we try it? Elementary. Maybe I put it in the lecture notes. And show. But I think there's not much to learn from this, that 2c times log c is greater than c times logarithm of 2c times log c. Maybe you see it directly, huh? Of course we can cancel c here. So we have 2 times log c. and you can use the rules for them. Okay, I think let's do it. Should be trivial, yeah? So 2 times log c is greater than, I cancel just the c, and then you have this logarithm here, and you can say that's log c plus something, and the something is logarithm of 2 times log c. And then you see that this was just the rules for logarithm here, that you can have a logarithm of a product, which is the sum of the values of the logarithm. And then you see that you have to show that log c is greater than log over 2 times log c, which basically means that c is greater than 2 times log c now we have to see whether c greater than e, c is greater than 2 times log c. Something like this here. Which I guess is correct. Well, you have it again for c equal to e. E is greater than 2 times log e, which is e is greater than 2. And you look at the derivative 1 here and 1 divided by c here. So the derivative here for argument greater than c will be less than 1. And we got it here. So at least I understood my proof. But you see, but that sometimes, what's behind big theorems, you come up, basically go back to analysis 1 here and make some stupid parts. Okay, questions? Question, please? No question? I put a complete proof in the lecture note, in the community plan. Okay, and now there's another case which I have to look at, but this other case is trivial. That's even better. So we come to part number 2, there's 1 here. Now we have 2. If this condition is not satisfied, so if b divided by epsilon times this logarithm of 2 times packing number lower bound. This is less than the reductive generators of dimension of G plus. Any idea what happens then? Well, you have an upper bound for the logarithms of the covering number, yeah? This gives you, of the packing number, this gives you an upper bound of the packing number. A little bit ugly on it is the Gauss bracket, but what can we do with the Gauss bracket? We have this Gauss bracket in here, yeah. We have this, yeah, because we have it here. But we know something about b divided by epsilon, yeah? B divided by epsilon is at least 4, yeah? Well, of course, I can write here -1, and then I have a vector mixture of x dimension +1, and okay. Yeah. Maybe write a -1 and bring it as a +1 on the other side, and so I make this +1. I forget about the Gauss bracket. I multiply it by epsilon divided by b, then you have the logarithm of 2 times epsilon g and 1 of mu. That's less equal than epsilon divided by b times factor of x dimension of the subclass +1. And then you see you see it? Okay. So look at this guy, 2, covering number. Is less equal than e to the power epsilon b g plus 1. And now I claim that this implies the assertion of theorem 3.5. Well, if you forget about the +1.
Question. We want to prove that two
We-
holds, right?
We want to prove that if this is satisfied, then the assertion is trivial. So I assume that this holds, I get a bound, and I want to prove that this bound is sharper than this bound.
I thought we needed 2 in order for lemma 3.1 to hold.
What do you mean? You mean corollary 3.1? No, I don't want to apply corollary 3.1. We had, in this case, we apply corollary 3.1 b, but now we cannot apply it, so we proved that it's trivial because we get directly the right bound.
Okay, yeah.
That's the point.
Fine.
So now you have this assertion, then you get this guy, yeah? Now, if you think for a moment that you don't have this +1 here, then maybe you see that it's trivial, no? Well, look at this guy. Epsilon less than b divided by 4. So this implies something about b divided by epsilon. It's at least 4. Here we have at least 4, here we have at least 4. So this means this whole thing is at least e. And this thing here is e logarithm of 12 times e. Well, that's more than 1 here. So the whole thing here is more than e. So the whole thing is more than e to the power Butler length dimension of the graph class. And here I have an epsilon divided by b, which is 1/4. So of course this guy is less than this guy. That's fine. If I forget about the +1. But what about the +1? Well, I also know something. I know the Butler length dimension is at least 2. So I can forget about this plus 1 by just making another bound by 2 times the Wagner-Chermanek dimension. Then I have an additional factor 2, but you have 2 times epsilon divided by b, and epsilon divided by b is upper bounded by 1 divided by 4. So this is less than e to the power epsilon divided by b times 2 times Wagner-Chermanek is not 4 is less than e to the power 4. That means 0 volts. And that was the technical part of this theorem, no ideas at all here. Next comes the real idea. Well, I told you there are 2 parts of star. Yeah? The first part is why does this imply the assertion? The second part is why does this hold? And the second part is the interesting proof, which I won't explain today. Or any questions up to that point? Which I will not explain today. Instead, I would like to ask you to fill in the questionnaire about the lecture. The address is well, you know this address, it's t1p dot e/mbe. And what you don't know is the Losung, what you have to enter. And the Losung is a V7 F7. So please go to this website, enter this Losung, then you can choose whether you want to answer this question on German or in English. There's a flag on it. And so if you don't speak German, you have to choose the English version of it. Then please fill it in. And I give you 12 minutes for it, and then the lecture is over. So thank you.